So we've covered how to deal with large sample sizes. We've covered how to deal with small sample sizes, but now we're going to start to ask questions about hypothesis testing. And there's a typical procedure. Again, we're trying to see whether things are statistically significant or not statistically significant. So again, kind of back to this question of if I have two samples, if my error bars are overlapping, they are statistically the same. I can't say, if this is A and this is B, while the mean of B may be larger, statistically, there's no difference between them. So we have to kind of understand and assess, essentially, are they statistically the same or different? Is one larger than the other? And we do this basically through hypothesis testing and through calculating our associated p-value. We'll get to that in a bit. So there's a couple steps in hypothesis testing. First step always is defining essentially your null hypothesis. And the null hypothesis is you establish, okay, the population mean is a specific constant value. The second step is you define their alternative hypothesis. Now, there's basically three different hypothesis tests that we're going to deal with: a two-tailed test, left-tailed test, right-tailed test. Two-tailed test is basically the alternative would be if our null hypothesis is equal to the second, or then the two-tailed test would basically be it's not equal to. So the alternative would be the mu of the population is not equal to, meaning is it statistically just different? Is it not equal to? You can also do a left-tailed test, meaning alternative is it's less than, or a right-tailed test greater than. We have a nice little kind of figure in our notes. Oops, I just changed that, but it's okay. We have a nice little figure in our notes where it kind of shows you how you can establish, and this little dashed line, I call it the theoretical kind of t-value here, versus where your experimental t falls into place. But we'll get to that back in a second. So when you're doing your hypothesis testing, define the null, define the alternative, define the confidence interval, calculate experimentally a t experimental value. Now your t experimental is just this here. X bar minus mu, and this mu is basically established from your null hypothesis, which is that mu is equal to some constant value mu naught. You plug in mu naught there, and then you calculate the rest from essentially the sample that you have. 6, you have to establish, or 5, you determine essentially what is your kind of your theoretical value is kind of what I typically will call this. And then you see, where does it fall? Does it fall in the reject region or do not reject region? So I think the best way to start is by doing an example. So we have a data set that's PCM data. We'll see that in the Mathematica notebook in just a second. Does it come from a population with a true mean of 2 milligrams? Assume a confidence level of this. So first step, null hypothesis, alternative, and now we need to start to calculate the values and our theoretical value as well. So let's go ahead and do it. So I've got some data files here. I'm going to actually, let's see if we can work side by side. That'd be the nicest. We can do that. So let's go ahead and I can go ahead and get this set up. So we've got our data file. This is our V is our rolling velocity, PCM, material A, material B. We're going to read in our needs hypothesis testing. And one thing that we can do right off the bat, what's happening here? Did I not? Oh, did I change the location of this file? Probably. Let's see. Ooh, yes, this is not. But I think I might have PCM already. Let's see. Let's just see if we get PCM. PCM first. That would be great. PCM. Let's see. Here we go. Hopefully we can find. PCM data file? There's the one way, the two way. Let's see if we may be able to find that in documents too. But I think I'm actually going to have to go through. Sorry for the delay. But I could find it would be great. PCM. I feel like it's somewhere in here, but I think it's reading it from the file itself. Give me 1 second, and I'm going to basically copy these, and I'll be back in just a minute. All right, everyone, we are back, and I just did the old trick of basically reopening it and saving the raw data file. So we got the PCM data file right here, as you can see. So we can approach this from multiple ways. So let's first do it. I want to show you the way that kind of you see this normally taught by calculating these values, comparing, looking up the tables, and getting that. So this is my t experimental value, x bar minus mu, standard deviation over square root of n. So I'm going to take the mean of my PCM. We're saying, does it come from basically a mu of 2, standard deviation, and length. So this is my t experimental value. Now, our T alpha, if it's a two-tailed test, is really alpha over 2. We're working at 95% confidence interval. This says 0.05. 0.05 divided by 2 is 0.025. And if we look at the length of our PCM, we get 18. So degrees of freedom is n minus 1, so that's 17. So we could go look in the table, see that this theoretical value, 0.025, 17, is going to be 2.110 right here. I don't know why it's picking blue. Right here. And then now we can say in our two-tailed test, okay, if this is minus 2.110 and this is 2.110, our t experimental falls right in here, so that should be a do not reject. So it should be a do not reject. Where can we go? Let me go back. And let's see, here we go. And it does fall within the do not reject region. So that's fantastic. Now we can take it a step further. So one thing is if you don't want to use the table, which I'd probably say, especially you want to move towards, probably programming this in, you could use this function called quantile. So it will take essentially the student t distribution. We have to specify in the student t distribution the degrees of freedom, and the quantile we have to specify 1 minus our alpha. So we need to specify the confidence interval. Now you see here I'm doing 0.05 divided by 2 because, again, we're doing a two-tailed test, so we just want that value either to the right or to the left here. So I need to kind of specify, if it was just an alpha, like a right-tailed or left-tailed test, I would just leave that alpha right here. But since we're doing alpha over 2, it is that. And we saw that when we looked in the table, it was 2.11, so very consistent. So we can use this to just automatically get the value if you want to do this method. Now, the beautiful part of Mathematica, and I think a lot of this, a lot of using the kind of programming tool is MATLAB too. Let's just say I wanted to get one value that tells me if it's a reject or do not reject, so I don't even have to kind of look up tables and all those things. Well, if I have the data set, I can run a t-test. So in Mathematica t-test, I can say, look at my data, PCM. I could say, does it come from a population of 2? And then I can spit out this test table and look, my t-value is the same as it is right here. And it gives me a p-value. This p-value, and actually if we go over to here, because I think graphically helps here. The p-value will take, so our t, if this was 0, our t was right here, 0.99. The p-value takes the integral from here to infinity. So this whole area. If my p-value is greater than alpha over 2 for a two-tailed test, for a right-tailed and left-tailed, it'd just be as p greater than alpha. If my p is greater than alpha, that is going to be a do not reject because I'm falling within this regime, right? Because I know this area beyond this dashed line, that is going to be my alpha over 2. So that, in this instance, would be 0.025. So if I fall within this regime, then when it integrates from here to infinity, that should be p less than alpha over 2. That should be a reject regime. So the p-value is kind of like your single value that tells you, are we in the reject or do not reject regime? So we always want to get to that p-value because that's essentially, the single number, and it simplifies a lot of kind of your analysis. So really, really, really important. Figure out the p-values, make sure you're feeling okay with that. So let's go ahead and let's keep working with our PCM. So now it's saying, is it greater than 199? So we can do the same exercise. We can do the t-experimental. I can find, you can see here, remember, still same t-distribution, degrees of freedom, length minus 1. Now I'm looking at a 99% confidence interval, so I just want 1 minus 0.01. That's going to give me my quantile. So automatically I can see here, if I look back at I'm doing a right-tailed test, so I'm falling in the do not reject regime, right? Because my theoretical value is larger than my experimental value. So I should fall in the do not reject regime. Now, before I even look, and we can see the answer below here, but we should know in this basically instance that I am going to deal with, and actually here's a really dangerous one too. My p-value is going to integrate, and actually I need to work on this. My p-value should be greater than 0.01 because we know it's a do not reject regime. Now, if I just do this, you see that the p-value it's given, it's not, this is assuming it's a two-tailed test. So the p-value is actually basically extending in a different direction. It's really interesting. And you can see here, this is not the value essentially that we're wanting or expecting. And actually we can see here, our p-value here should be this. If we're working on a right tail, left tail test, we have to specify. So if we're looking at greater or less, we should see that that's much larger. Makes sense. But if we're only looking at the greater side, if we're not essentially integrating essentially both of those sides on that p-value, then essentially we want to get rid of that. So make sure you specify if you're doing a right tail, left tail test, that alternative hypothesis method there. Very, very, very important. So be sure that you're considering essentially that case. So fantastic. Now, let's go ahead and let's do, and actually we can double check with that last one, 0.336, and we have that same value there. Fantastic. So what about less than? Well, kind of same idea. One big thing is if you're using your information for your quantile, when you do a left-tailed test, and if you're kind of trying to visualize it here, it has to be negative that quantile value. So for example, our t-experimental is minus 0.043. This should be minus 0.133. So you visualize it that way. So we should fall in do not reject region, meaning that, in this instance, when we're looking at a confidence interval of 90, so 0.1, our p-value must be greater than 0.1 because we're failing that test. So again, you can kind of look at that. We want to look at the alternative hypothesis because this is not getting us what we're looking for. And we can see here 0.4823 greater than, so that is indeed a do not reject. And we can kind of see in consistent values. So that's the nice part. So that's great. What happens if you're dealing with a large sample size? Well, the only thing that changes is instead of, you can still do the t-value, but you're basically, if you're looking at your degrees of freedom, it can go to infinity. So if I'm looking at less than 3.1, confidence interval 99%, I can calculate my t-experimental value as you see here. I can get my quantile. Now here you're going to see, look at my theoretical value versus the one where I assume it's at infinity. Slightly different, but again, fairly close. So again, if you're using the tables, if you're a large sample size, you can just jump straight from 30 to infinity. But that's essentially where that little difference is coming from. It's not a huge deal, but if you want to be more accurate, the quantile is a nice approach, especially depending on what you're trying to measure. And we can see here, if we're doing a left-tailed test, this is, again, negative, so it's less than. This should be a do not reject, so that should be greater than, and that's a typo there, because this is not 99%. Oh, it is 99%. So this should be greater than 0.01. So we should, again, once again, a do not reject. And we see indeed it is 0.01. Fantastic. Now, what about the following scenario? We've been talking a lot about, like, does this sample come from this population? Does this come from this? A lot of times you want to be able to compare things, right? Like in that first example I showed you, it was like A versus B. We want to be able to compare, is this sample greater than this? Is this sample different from this? Are these two statistically significant? We can do the same type of t-test. However, as you can see here, the only thing that changed in our hypothesis testing protocol, t-experimental becomes very nasty to work with, but it's just an equation. And your degrees of freedom is no longer just the number of samples minus 1, because I have 2 different samples with potentially 2 different number of measurements, et cetera, et cetera. So let's look at material A and material B. Are they statistically significant? So you can see here, null hypothesis, the means are the same. The alternative, they're different. So I can do T experimental. Order matters here. So whatever you decide, if this is A and this is B, then it has to be A, or B, 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 respectively, right? So means, standard deviations, lengths, I got my T experimental. I can calculate my degrees of freedom here. I can also approximate basically my that theoretical T value, right, with my quantile. Just note the quantile, I have to bring in this new from here, where it doesn't specify, or maybe does it specify? It doesn't specify, so we assume 95% confidence interval. It's a two-tailed test, so that is 0.05 divided by 2. So that is going to be our theoretical value. Very similar, so that's good. And we can do a t-test. So if I have material A, material B, 0 is basically saying that are these, are the samples basically, how should I put this? I'm failing at this at the moment. My brain is, are the means of the 2 samples, is the difference between the 2 means, is it 0? So that's essentially what we're asking for here. So when we do that, we get our T statistic is the same here. We know from here that this is going to fall as a do not reject. So we should expect the p-value to be greater than 0.025. And indeed it is. And we get that 0.162 value. And that's all. And that's it. So you can do similar. The only thing that changes that process is just the equations. You can do greater than and less than. And we will see you all in the next video. Thanks. Bye. One last thing, and it's a very important and it's a very subtle kind of notation thing because of when you're programming Mathematica. We've been saying here where it's like, okay, if we're calculating the p-value from this specific number and we go to positive infinity, for a two-tailed test, if p is greater than alpha over 2, then it's a do not reject. One thing is if you're using Mathematica to calculate, which I hope you all do, that p-value, and if you're doing a two-tailed test, so for example, let's look at this. If I do, let's say I'm doing the PCM, let's say I'm saying, is it equal to 2.03? We know that this value is negative. If we were to do the quantile at this confidence interval of basically 0.025, which is very reasonable to do so, we know that this should be a reject region, right? So, but if you calculate this, right, this is giving us a p-value of 0.0495. Now, it's just barely a reject, right, because it's just to the left. However, if you're going on that strict definition of the 0.025 magnitude value, right, this would indicate a fail. But if we look at it and just say, well, if you're doing a less than, it's less than 0.025 here. So basically, this is doubling. So that p-value, if you don't specify an alternative test method, so for example, if I just do alternative hypothesis, unequal, it's going to double. Do you see that? And if I go greater, it's going to integrate almost the full length. So if I do less, I'm just going to take this times 2, and that's going to give me essentially the value in here. So if you're just doing this or you're doing an alternative test unequal, it's just giving you the double value. So if you're using Mathematica, you want to say, basically, even in this instance for the two-tailed, and actually it's great because it's kind of simplified, all of these will be p is greater than alpha. That will give you a do not reject. If p is less than alpha, then that is a big old reject. So just to be consistent, if you do it with some other codes, it may not see or show it that way. So just be there or be safe, double check that, and you can kind of see those values. So be careful out there. That's why it's fun. I mean, we don't want these tools to be a black box. We want to be able to test and find these things. So alternative less, greater than, and you can do the same thing with basically right here, greater, less, for a two-tailed test as well. You don't even have to specify essentially the 0. Although you probably maybe could. and it doesn't change anything. Yeah. And then if it's unequal, we should get the same value here of the 0.16. So fantastic. So that's pretty much it. So we'll see you in the next video. In lecture 3, when we get into, because we have finished lecture 2 now, we will get into air propagation and ANOVA analysis. So we will see you then. Thanks. Bye.